Hello all, as we continue to look at polynomials. This is our final exercise for the chapter. So like always, we're now finally getting into actually applying our skills to real world problems as much as we can probably call them, even though they're still a bit contrived at this year 11 level. It's giving you an idea where this is going towards. All the notes here are pretty much exactly the same as when we did applied quadratics. Okay? Because it's the same thing, just with a slightly different graph. And same when we did applied gallery of graphs. Exactly the same thing, just another different type of function, and that has a slightly different shape. So let's roll through all these points. This exercise may appear tricky, but ultimately these questions are just polynomials that have been disguised in some way. In the easier questions, the equation is given to you. Get an idea for the shape of the problem, even if this means just roughly sketching out so you can sort of imagine the scenario. And I'll talk about that a little bit more in the next example. If the question doesn't give you defined variables, then as I've said previously, you must define them. You must let me know. If you start using x's and y's and the problem hasn't told us what x's and y's are, you must let me know what they are. That's part of communicating clearly. Remember, maths is just communication of ideas, so you need to communicate clearly and leave no ambiguity. Due to the complex nature of higher order polynomials, some of the problems will require the use of CAS calculator to solve a system of equations or find turning points. This is exactly pretty much what's on application tasks and tech active exam things. It's testing your ability to interpret information given to you that's a bit more complex, or find information quickly using your CAS and knowing what information is that you're trying to find. And I can't stress this enough, don't be a hero and try and do that by hand. I'll talk about in all these examples going through the rest of this exercise, it's all tech active. Let's just set it in stone for now. We'll go tech active. It is good to go back and practice every once in a while, maybe how to factorize or how to find the intercepts or solve for the equation when it was equal to something. But for this, we're going to go, it's tech active with the assumption, having done all that prior work, that you do know how to do it. And if you ask to do it by hand, you can. But for the sake of brevity in this video, we'll go tech active. Pardon me. So a big part of it comes down to using this CAS, making sure you can, let's clear all that. Yeah. Okay. Using your CAS. Right here. A square sheet of tin measures 12 by 12 centimeters, and 4 equal squares of edge x centimeters are cut out of the corners. The sides are turned up and folded to open to find open to make a rectangular box. Find. And then we have all the following parts. So what's essentially happening is the tin, or we could imagine this cardboard like a shoebox, is being folded along those dashed lines, and then once it's folded up, we're getting a three-dimensional shape like that, with an open top. Okay. The values of x, which the volume is 100 centimeters cubed. So this is jumping a fair way into the problem. This isn't saying find an equation for the volume or anything like that. This is making you jump a little bit ahead and asking straight away for 100 centimeters cubed. So what we're going to do is we're going to put some writing down here. We're going to put some stuff into our CAS, and then we're actually going to list what are the CAS functions used, so that you're starting to get an idea what are the things that are popping up really common, and what are the things that I really recommend that you do with your CAS. So first off, we need to find an equation. Now we're already told that we have this edge here is called x, so we don't need to define that at all. We're going to let v equal the volume, and we're told that v is going to equal 200 centimeters cubed. That should be cubed, by the way. Okay. what else do we need to do? Well, we need to make the equation. Well, the volume of a rectangle is length times width times... The volume of a cube is length times width times height. Rectangular prism. So let's have a think about what is going to be the length, the width, and the height. And let's come back maybe up to our diagram up here. So our length is going to be across there. Our width is going to be across there. And then by folding it up, our height is essentially the x. Because once that's tipped up, pick a different color. Once that's folded up, that distance there becomes your height. Sorry for the random pause. My wife just called, so I had to take that. All right. Where were we? Length, width, height. So we know what a height is. That is x. We can put x in there. We need to figure out length and width. Well, the total width all the way across was 12. And we've taken a chunk out there, x, and we've taken a chunk out there. So we can say length is equal to 12, and we're taking away an x, so we could say that is 12 take away 2x. Because we've cut out a chunk x from each side. And the width is exactly the same. We've cut out a chunk x there, we've cut out a chunk x there, so width is equal to 12 minus 2x. So we can substitute that in. So we now get volume is equal to 12 take away 2x times by 12 take away 2x times by x. Now, it would be nice to have that in a simplified form, but this is CAS active. So let's start going to our CAS, and very first thing we want to do is we want to define a function. We want to store it. Define means store. Give this thing a name and store it as that so we can recall it as much as we want. So that is in Math 3. So we're going to define, and we're just going to call this a function of x. Now, even though you may be working, a problem might be dealing with time over here. We might have like v's got something to do with time. You always want to store in your CAS as x instead of whatever other variable you're using, because you can only graph functions of x. You can't graph functions of t in a CAS, you can't graph functions of a, you can only graph functions of x. So store it as a function of x, so f of x, g of x, h of x, whatever you want to do. Well, what did I just press there? That zooms in and out on PowerPoint. Okay, so f of x is equal to, and we're going to go 12 minus 2x, bracket 12 minus 2x, and x. And what we should do to get in good habits is put a times sign in there, and a times sign in there, because sometimes the CAS doesn't interpret it quickly, and we can go done. Now we can also now just type f of x, and it'll give us back the function. And as you can see, the CAS automatically simplifies everything for us. So we could now say volume is equal to x, 2x minus 12, all squared. It is simplified for us. So from there, we want to find out what x is when the volume equals 100. So we're just going to let 100 equal to x, 2x minus 12, all squared. So to do that with our CAS, we're trying to solve an equation. So we go back to Math 3, and we're solving, and what we're doing, we're solving f of x in our case is equal to 100, and what are we trying to find at the end of all that? That is x. There we go. So we get a whole bunch of values here. We can also click on standard and change it to decimal, and click back in our line and hit enter, and now it's going to give it to me in decimal. places. So what are the functions that we used? We had define f of x, and then we did solve f of x is equal to 100 comma x. Okay. Now you wouldn't write this on a SAC or an exam, especially year 12. They don't want to see that actually. They're not going to take marks from you, but they don't want to see it. It just assumed that that's what you're doing. So what you'd be writing is some of this over here on the left. You'd be writing some of that, and you would do this. Okay, we figured out our volume, and then you'd write this let blah blah blah. Where was it? Squared, and then from that we get x is equal to 1, 3.208 or 9. It should be rounded up, and 7.791. Okay. Now, quickly, can x actually be 7.791? Well, if it was, that whole distance across there would be like 15 point something. So that doesn't work. So we reject that answer. And you might even want to say, reject, not valid. And then we're just left with x is equal to 1 or x is equal to 3.209. Now, why are we getting two answers? Well, as we change x, it's making the base smaller, but it's making the height greater. And it'll be doing something where as we change x, and we notice we've got an x and then an x in the squared, so this is going to be some cubic. It's going to be doing something like that. And now 100 volume is there. So we've found that one, that's 3.209. And that is 7.91, but we can't have an x greater than 6. Okay, find the maximum volume. Now, at the moment, we haven't done differentiation, so there's this whole thing tied around. You can always find where any turning point of any function, quadratic, cubic, anything you want, you can find the turning point using differentiation. Now, we haven't done that yet, so it's just a matter of using our CAS skills. So again, we'll go back to our CAS. So since we defined it, it's actually really nice and easy. We can go y1, and I already had it typed in, but we can just type in f of x. Click enter, and then I should change as to default. Let's go that. This is what it would normally look like, and we're getting this bit. And it's like, oh, what's going on? We need to change our zoom a bit. So let's go to our window, and our x is fine. We can only deal with between 0 and 6 realistically for x. But our y value, well, clearly we were told our volume, we found it can be up to 100. So let's set that to maybe 150. A y value, and there we go. Now we can see the curve, and I'm just going to go back to my window and change the scale to 10. There we go. That makes it a lot nicer to see. So we can see our volume, how our volume changes as we change our x value. Our y is technically our volume. So from here, our max that can occur is at this turning point. It's not going to be at this line on the right as it keeps going up and up and up because, well, we said we can't have an x greater than 6. So how can we find that? We can do analysis, and from this we want gsolve max. So analysis gsolve max, and it's instantly found us for us. So it occurs at 2,128. So all we would say here is max volume is equal to 128 centimeters cubed at x equals 2. What were the CAS functions used? Well, we graphed, and then we did analysis gsolve max, and it found us for us. So nice and easy. Rightio. And so that's a quick look at using our CAS, solving problem. because it might be, right, that's because of the material I can only buy it in 12 centimeter shapes. I want to maximize the volume of the box. What should I make x equal to? Well, there we go. We just found we should let x equal to 2. And that gives us a volume of 128. So let's go on to another example. It is found that 250 meters of the path of a stream can be modeled by a cubic function. The cubic passes through the point 0, 0, 122, 150, negative 10, and 200, negative 20. Okay, so what I'm going to do is, these are given us to in coordinate form, so we get to assume that this is x, y. So, and I've even put into the slides a little axis, because this is one of those ones where sketching some points to at least have an understanding what is this shape looking like roughly. So it starts at 0, 0, 0, goes all the way up to, let's say that's 200 there. So 100 is there, goes up to 22. So we'll say that's there, that's 100, 22. 150 is there, negative 10, so about there. 150, negative 10, and then it goes to 200, negative 20. Okay, so the river is roughly looking something like that. And then very first one is find an equation for the cubic function. So, because we're told it can be modeled by a cubic function. So let's let y equal to ax cubed plus bx squared plus cx plus d. That's a basic cubic function. That's the general cubic function. And we have 4 unknowns in it. Now we're also told 4 bits of data. So we can solve this, and we can solve this using simultaneous equations. I'll go back to my main. So what are we doing? I'm going to, again, and I'm going to jump straight over to my CAS. I'm now going to define a new function, and I'm going to call this one g of x. Now we could go back and call it f of x again, but I'm going to keep that just in case I want to go back and check my work later on. But we're going to define g of x, and I'm going to define it as a, and now we're using the Casio ClassPad is a little bit weird because it has 2 different sets of letters. It has the variables A, B, C, and you can see if I click on B or if I click on A, they're in bold. So that's assuming that that's always going to be an actual variable where I can put numbers into it. If I use the ABC keyboard, which is what's happening when I'm typing on my actual keyboard on my computer, I get these sort of non-bold letters. If you put in AX like that, that assumes that's actually a single name, not 2 separate variables. It's just a single thing named, and the CAS runs into problems. So it's a little bit tedious with putting in when we have X and other letters in an equation or a function or expression that you're putting into CAS. It's a little bit tedious putting in, but here's the best way to do it. I go back. So you go to in your keyboard, go to ABC, and we'll put A, and then you're going to use the X on the main keyboard of your CAS down the bottom. And you can see that's put it in as a bold X. And now that's going to differentiate between A is one thing while X is another. And that's going to avoid any confusions from the calculator. And that is cubed plus, now I go back and put a B from there, x squared plus cx plus d. And I can hit enter, and then if I want to check, I can just type g of x, and there it is there. And it's also, because I've used the 2 different types of lettering, it has recognized they're different, and it's put the time signs, the multiplication signs in there automatically for me, those dots being multiplication. Right, so I've defined it. What do I need to now do? Well, I need to just use the bits of information that I'm given, those 4 data points, and substitute them in and solve using simultaneous equations. Now, you're not going to go g. The way that you substitute in doing this whole g of x, f of x thing is that, well, g of 0, we're told, is equal to 0. That's letting x equal 0, and we're told it's equal to 0. That's one equation. We also have another equation where we're told when x is 100, y becomes 22, or g of x becomes 22. We have also 150 is equal to negative 10. So that's the sort of notation we can put in. So how do we write that on the test versus how do we do it on the calculator? Right, I would and I would just do sort of 0 equals, and I'd write it at substituted in. So we get 0 is equal to a by 0 cubed plus b by 0 squared plus c by 0 plus d. And I'd do that for all of them. So we get 22 is equal to a by 100 cubed plus b by 100 squared plus c by 100 plus d. And you'd write that out 4 times. And from that, you could just go over here. You could just use the follow-on symbol, because it's assumed in a tech active thing, it's assumed that you're just going to use your CAS to solve this set of simultaneous equations. So you just write the therefore symbol, and then you're going to write the answer that you get from your CAS. How do we do this on the CAS? Well, we need to use the System of Simultaneous Equations solver. It's a thing on the CAS. Now, there is the solve over here, but that solves a single equation. We need to solve a system of equations, and that is in Math 1, and it's there. It's next to this 2DMS button to the right of it. Now that gives us a solver that will solve 2 simultaneous equations, but in our case we have 4. How do we solve 4? Well, after you press it the first time, press it again, you get 3, press it again, you get 4. And that's going to let us now go g of 0 is equal to 0, g of 100 is equal to 22, g of 150 is equal to negative 10, and g of 200 is equal to negative 20. And now we have to again put in, like the original solve tool, we have to put in, what are we trying to find? Well, in our case, we're trying to find a, comma b, comma c, comma d. That's what we're not trying to find x, we're actually trying to figure out what a, b, c, and d are. From g of x, hit enter, and bam, there we go. Just got to be careful reading it. What does this e to the negative 5 means? Well, that means times 10 to the negative 5. So let's just go through and read those. So we got a is equal to 5.066 by 10 to the negative 5. We got b is equal to negative 0.0184. C is equal to 1.553. And D is equal to 0. So what we use for our CADs, we use define, and we use the solve system of linear equations, which was, it looked like this. It actually doesn't have that second box. So that's what we used. And so we found the equation. There's the equation. Find the maximum deviation of the graph from the x-axis for the range, that's what else, for the domain x between 0 and 250. So again, this is where you need to just graph it, and then we want to find the maximum deviation. This means find the maximum distance the graph gets from the x-axis. Where's the maximum or the minimum point? Because it's asked for deviation, so just it's the maximum distance, so therefore it could technically be a minimum below the axis. Right, so let me go back to standard form, because generally it's nicer to actually use this graph in exact form. So it's much easier to write this as we're going to have to restore these numbers. Even though we found A, B, C, and D, it's not going to actually store them in the CAS if we try to use G of X. So we couldn't now do G of 2. It's not going to work. It's going to leave the A, B, C, and D there until we redefine G of X using these values of A, B, and C, and D that we found. So we're just going to go back to math 3 define. We're going to store it G of X is equal to, and this is the handy thing, you can highlight the fraction, bring it down, and then put X cubed plus, actually we'll leave the sign off because it's got minus sign there, minus 23 X squared. Oh, I need to get the right X. And plus, let's click across, make sure we get all fraction, drag it down, X and D0, so we don't even need to put that in. So now we've got G of X stored properly. And to find the maximum deviation, we're going to go back to our graph, Y1, and we're going to now graph G of X. Hit the graph button, and it's going to start graphing. Now again, our zoom is not useful, so let's go to our zoom window and think about what are the ranges that we need. What's the domain and range that we need? Well, I always leave in a little bit of negative, even though we don't need it for this. Sorry for another interruption. Wife called again. Right, what were we up to? Finding maximum deviation. Oh yes, talking about the window. So yeah, I leave a little bit of negative on the X just so I can see the axes. Makes it easier. X max, well, I want to go up to 250 because that's what I'm told in the problem. What are my likely Y values? Well, I've already know my max at the moment was 22 and my min was negative 20. I'm going to just go negative 30 just to give me some margin, and positive 30 as well, and see how that looks. And as I can see, my graph ends up going much higher and lower than that. So I'm going to expand that range. I'm going to go negative 50 up to 50. Okay. There we go. And I need to set across to 250. Okay. Rightio. And there we go. So there's our graph. So we can see the highest point is occurring somewhere around, and I need to change my X scale. Let's change that to 25. There we go, much easier to see. So we can see our first max is occurring around 50, and then the minimum occurs around the 175, and it's clear to see that the deviation is much larger at the 50 point. So we want to find the maximum, so we're just going to go G-solve again, max, and it's found the max for us. And that is 54.461. So max is equal to, max is actually equal to 30, because it's the Y value, 38.206 at X is equal to 54.461. And there we go. What was our CAS functions that we used? We did graph, and then we did the analysis /G-solve/max. And that's it. There's a lot in that. I cannot stress enough how important this solving simultaneous equations function is. That is massive, and you will use that throughout the rest of the year heaps, and it gets used next year in year 12 all the time. The first SAC is almost all down to being able to use that effectively and quickly in year 12. So yeah, that's it. If you have any questions, feel free to ask in class, put in the comments below, email, or put in Google Classroom. Otherwise, have a good day. Again, a little apologies about interruptions, but there it is.